is a video I am making about math because I don't know how to write a math paper. Okay. Okay. So here's a big idea. Uh, let's say you multiply two numbers together, two numbers of any size, right? The probability that you get an even number as your product is going to be 3 out of 4. Okay. Uh, there's one. There's more than one way for us to prove this. If you ask, what's the chance to multiply two numbers together and get a number not divisible by 2, the answer is going to be 1 out of 4 because this can only happen if you multiply two odd numbers together, right? Okay. The probability that you get an even number then is the chance the chance that you don't not get an even number, right? So that would be, write this down. Yeah, it would be 1 minus 1 over 4, which is equal to 3 over 4. Um, and 3 over 4, coincidentally, is also 2 squared minus 1 squared over 4. Uh, and that's something I want you to remember. Okay. Now, there's a way to do this that looks a lot nicer. Um, if you multiply two numbers together and you only care about if they're even or not, then there's only 4 unique multiplications that represent every possibility here. You can multiply two odd numbers together, an odd number with an even number, an even number with an odd number, or two even numbers together. And sure enough, if you count the odds and you count the evens, you'll see that there's a 3 out of 4 chance that you end up with an even number. Great, okay. Uh, Now there's a better way to write this that I want to introduce here. Some of you, maybe hopefully most of you, have heard of modular arithmetic. Um, if you don't know what modular arithmetic is, maybe you want to look it up or just watch this video when you get older. Um, if you know what modular arithmetic is, you know that every number is congruent to either 1 or 0 in mod 2, just like every number is either odd or even. Right? Uh, Odd numbers are congruent to 1 in mod 2, and even numbers are congruent to 0 in mod 2. So with that in mind, I'll redo the chart. It's right here. Now you should know that any number that's congruent to 0 in mod n is a multiple of n. So if we count all the zeros in this chart, that's the same as counting how many numbers are a multiple of what we're looking for. Okay, um, and I'm doing the chart like this from now on because that's going to come in handy later. You'll see. Right. Um, yeah, 3 out of 4 chance. Right. Great. Now, what's the chance to multiply two numbers together and get a multiple of 3? Like before, we can consider the chance that we don't get a multiple of 3. In order not to get a multiple of 3 as our answer, both numbers need to not be a multiple of 3, which is a 2 out of 3 chance for each number, right? Uh, this means that there's a 4 out of 9 chance not to get a multiple of 3, and so there's a 5 out of 9 chance to get a multiple of 3. Again, you can think of this as 3 squared minus 2 squared, then divided by 9. It's the same as before. Um, this way of calculating the probability will work for any prime number, and it's how I'll calculate the probabilities for prime numbers going forth. Okay. Now, let's do a chart to visualize this. Okay. Every number is either a multiple of 3, one more than a multiple of 3, or two more than a multiple of 3. So there's 9 possible unique multiplications that we can do here. Uh, if you count up the zeros, that's the multiples of 3, right? There's 5 of them, so it's a 5 out of 9 chance, which is what we found before. Um, okay, now I want to show you a different way of solving this, another different way. Let's say we make, oh, 5 out of 9, okay. Let's say we make three groups, right? I'll call this the one group, the two group, and the three group. In the one group is 1 times 1, 1 times 2, and 1 times 3. And the two group is 2 times 1, 2 times 2, and 2 times 3. And in the three group is 3 times 1, 3 times 2, and then 3 times 3. The one group, so these groups are supposed to represent, just like this chart, it's supposed to represent every possible multiplication you can do. So this one group, it contains one multiple of 3. The two group contains also one multiple of 3. So this, and the three group contains 3 multiples of 3. If you add this up, it's okay. If you add this up, it's 5. That's 5 out of 9. Okay. Now let's introduce some notation for this. If I want to multiply, let's say, n numbers together and find the probability it's divisible by a number x, I'll write it like this. Hold on. Since the denominator of the fraction, right, it's always going to be x to the power of n. Like right here, it's 3 to the power of 2. It's 9. We already know what the denominator is going to be. So I'm just going to make f of x with n represent the number of multiples you get. So the numerator of the fraction. And then in this case, I'm multiplying two numbers together, and I want to find the probability it's divisible by 3. So I write it as f of 3, and then n is equal to 2. That's equal to 5. Okay. Now, what about f of 4 for two numbers? We can write out the 4 groups once again. Groups 1, 3, and 4 make sense considering what we've seen before. What we've seen before. But group 2 here is new in that we get 2 multiples of 4. Right, it's this one and this one. So let's find out why that is. 4 has 2 prime factors. It's equal to 2 times 2, right? When you're asking the question of whether a number is divisible by 4 or not, you're essentially asking the question of if a number can be divided by 2 twice. And these end up being the exact same question, right? So in group 2, since all of these second numbers are being multiplied by 2, the requirement shifts from needing a multiple of 4 from the second number, right? Like you have here, to only requiring a multiple of 2 from these numbers. And that's why we get 2 multiples of 4 from this group. Hope that makes sense. All right. 1 plus 2 plus 1 plus 4 is 8. So there's an... That's okay. It's an 8 out of 16 chance. I wrote 4 out of 8, but I don't want to go back and change it. Okay. Yeah, it's an 8 out of 16. Oh. It's an 8 out of 16 chance to get a multiple of 4, because 1 plus 2 plus 1 plus 4 is 8, and then there's 16 multiplication. Okay, so I'm going to skip 5 now because 5 is a prime number and we've already, figured out how the prime numbers work. I'm going to move on to 6 now to find f of 6. What is this? Okay, so let's look at the chart. Groups 1, 5, and 6 all make sense based on, what we've seen so far. So what I want to focus on here are groups 2, 3, and 4. Now, crucially here, there's something I want you to recognize about this, because here, suspiciously, the value that we get for each group is the greatest common denominator of this group's number and the x that we chose. this isn't a coincidence, and we can come up with a pretty good reason why this is true. In group 2, since everything's being multiplied by 2, all you need is a multiple of 3 in the second number, right? Um, this means that we're asking the question of how many multiples of 3 are there less than or equal to 6? And the answer to this, of course, is 2. Um, in group 3, it's the same, except we're asking how many multiples of 2 are there less than or equal to 6? And the answer to this is 3. So let's see now why this is. Oh, okay, whatever. So these add up to 15. So f of 6 is 15, and then, yeah, 15 over 36 chance. Group 4 has a value of 2 because 4 also shares a common denominator of 2 as 6. So this group is going to, behave the same as the 2 group. So I put the same number. Okay. Yeah. Okay. So just as a general example, imagine a number x that's a multiple of two numbers a and b, right? If I ask how many multiples of a are there less than or equal to x, the answer is going to be b, right? Because this is a times b. And then it's this 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 question is it's the same as what's happening here. Um, maybe that makes sense. I don't know, but I think it explains this. Um, but what this means by this pattern, the lowest common denominator, right? It means that we found an easy way to find f of x for two numbers for any given x, right? Because f of x is simply the sum of the greatest common denominator of all the numbers under x with x. So it's, you know, greatest common denominator of 1 and 6, of 2 and 6, 3 and 6, 4 and 6, 5 and 6, 6 and 6, and then you add it all up, and that's the number you get. Fortunately, for it's fortunate that this is already a function that exists. It's on oeis.org, and it's called the pli function, and I'll probably reference it later on in this video. Okay, yeah, so that's f of x for two numbers. Now I want to look at what finding the values of f of x for three numbers would look like. Find f of 6. Okay, so we can do the same thing as before here. There's 216 unique multiplications possible in modulo 6, and they look like this. It goes from 1 times 1 times 1 to 6 times 6 times 6. Um, just looking at the first group here, multiplying all the numbers from 1 times 1 times 1 to 1 times 6 times 6 is just the same as multiplying all the numbers from 1 times 1 to 6 times 6, which is something that we did, what is this, 2 slides ago, and we got 15, right? So we can say for sure that this first group is going to have a value of 15. Okay, the second group is a bit different, something new, but there's a trick we can use here. If we ignore the first number while remembering that all of these numbers, the last two, are being multiplied by 2, this becomes a question of when you multiply two numbers together, how many of these make a multiple of 3? Okay, does that make sense? This is a problem we've solved before, actually, and we got an answer of 5, right? But the thing is, this answer of 5 results from multiplying the numbers from 1 to 3 all 9 possible ways. But in this situation, there are 36 multiplications, and they contain these 9 multiplications we did before 4 identical times. I guess you just have to trust me on that. I don't know. Or figure it out yourself. Do whatever you want. Since these 36 numbers contain the 9 multiplications 4 times, we multiply this number 5 with 4, and we can conclude that this group contains 20 multiples of 6. All right. The third group works the same. Since there's a 3 in front of these numbers, we just have to wonder how many multiples of 2 are in these 36 numbers. And since we got 3 out of 4 before, there's going to be 3 times 9 multiples, which is 27 in this group. All right. The fourth group is going to be the same as the second group because it shares the common denominator of 2. It's 20. The 5 group is the same as the 1 group, which is 15. And in the 6 group, it's pretty obvious that all these numbers are going to be multiples of 6. There's 36 numbers here. Yeah, there's 36 numbers here, so this group has a value of 36. Okay. 15 plus 20 plus 27 plus 20 plus 15 plus 36 is 133. And sure enough, if you try doing all 216 of these multiplications on paper, you'll get exactly 133 multiples of 6. And, that's why I'm kind of so confident that I'm correct about this. Now, this is how we'll calculate f of x for more than 2 numbers from now on. You reference the values from the previous amount of numbers. So here it's the values of f of x for 2 numbers, and then you use that to create the new values. Okay. Now I want to point out something pretty beautiful here. F of 2 for 3 numbers is equal to 7 because 2 to the power of 3 minus 1 to the power of 3 is equal to 7. And f of 3 for 3 numbers is 19 because 3 to the power of 3 minus 2 to the power of 3 is equal to 19. Now, 2 times 3 is 6, right? But 7 times 19, as it happens, also multiply to make 133. So what this means, right, if you include the denominators in all this, is that the chance for something to be divisible by 2 here times the chance for it to be divisible by 3 is equal to the chance for it to be divisible by 6. And that kind of works out, if you think about it. Because in order for something to be divisible by 6, it would have to be divisible by 2, but then also it would have to be divisible by 3. Okay, so since these values of f of x can multiply, right, to make other values, that would mean that this function is multiplicative, you could call it. We have a plan to calculate f of x for any given number. Okay, if we can find a way to hold on. If you break x into its prime factors, right? The prime factors here with the powers. If we can find a way to calculate f of something for any prime power, then we could divide any number x into its prime power, plug each of these prime powers into the function individually, and then multiply their outputs. Then we could calculate f of x for any given number for any number of numbers. Um, so that's the plan. Oh, okay, but sorry, hold on. You're looking at how long this video is, right? And you're thinking, wow, why is this video so long? Ugh. Out, it's going to be a lot harder to find f of x for a given prime power than, you might think. Um, Let me demonstrate this. Okay. Consider this. If I want to multiply three numbers together, how many ways can I get a multiple of 8? Um, well, the first number could be divisible by 2, and the second number could be divisible by 4. The first number could be divisible by 8, and the last two numbers could be, absolutely anything. All of the numbers could be divisible by exactly only 2, maybe divisible by more, and there's really no end to how many ways there are to make a multiple of 8 given these numbers. This is just thinking about three numbers, right? But if we wanted to find the probability of multiplying, I don't know, 20 numbers together and the chance it's divisible by 17 to the power of 5, sure, right? That's going to be a lot harder for us to figure out. So the way that I came up with to solve this problem is to generate all the values of the prime powers, generate a bunch of values for f of x given prime powers, and then try to find a pattern within these that we can use to generalize a formula. Okay, oh, I wrote that down. Great. Yeah, that's what I'm going to do. You can read that. I don't know. Okay. So generating, I'll call this f of p to the e. P is going to be p is going to be a prime number, right? And e is going to be the exponent it's raised to. And these are both variables in our equation. So based on what we did before, finding f of 6 for three numbers, we're going to use these numbers to generate the values of f of p to the e for three numbers, and then we'll use those numbers to generate the values for four numbers, and so on. Okay. Great. So let me just show you quickly how we're going to do this. Let's find f of 3 to the 2 given three numbers. There are three types of groups here. There's ones that have a common denominator of 1 with 9, right? Like this one, the ones that aren't divisible by 3, right? Ones that have a common denominator of 3 with 9, so that's a 3 and a 6, and ones that have a common denominator of 9 with 9. Hold on, lost my place in the script. Okay. The groups that have a common denominator of 1 will have a value of 21 because f of 3 to the 2 in two numbers is 21. And then this is effectively the same question. So these all have a value of 21. And there are 6 groups of this kind. Okay. The groups that have a common denominator of 3 will have 45 multiples because f of 3 for two numbers is 5, and that was for a group of 9, like a basket of size 9. But this is a basket of size 81. So we multiply by 9 to adjust. Sure, okay. The ninth group, this has 81 multiples because every number here is a multiple of 9, and there's 81 numbers. Oh yeah, two groups, sure. 81. Okay, so there's six groups of this kind, two groups of this kind, and then one group of this kind. Um, okay. Okay, yeah. So these add up to 297. So that means there's a 297 over 729 chance to multiply three numbers together and get a multiple of 9. You can try it. Let me know. Don't do that. Okay. Okay. Now, there's something I want you to notice here, which is that the number of these types of groups, they follow a pattern. There's one number here that's a multiple of 9, right? Oh, my nose. There's two numbers that are multiples of 3, and there's six numbers that are multiples of 1. So the pattern I'll describe for you here, um, there's always going to be one number of the highest possible prime power, then one less one less than the prime number of the next highest. So 2 is one less than 3. That's what I'm saying. And then the next number here is 6. 6 is 2 times 3. And then this is the pattern it follows. I'll show you a better example right here. Consider the number 14,641, which is 11 to the power of 4. The number of numbers divisible by 14,641 equal to or less than 14,641 will be 1. The number of numbers only divisible by 1,331. This is 11 to the power of 3. It's the next lowest prime power. Okay. There's 10 of them, and 10 is one less than 11. Okay. Next, there's going to be 110 of 110 multiples of only 121. It's going to be 1,210 multiples of only 11, and then 13,310 numbers that aren't divisible by 11 at all. And then this pattern, you see it follows. This exists for every prime power. That's what we'll assume. I won't bother proving this is true for all prime powers, but there's no reason to believe it isn't. So I'll use this fact to generate values of f of p to the e from now on. F of 7 to the 4 given three numbers. Like before, there are 2,401 groups of numbers that represent all possible multiplications that we can do here. Now, of these groups, there's 5 types, and I've listed here how many times each of them occur. Now we're going to find how many multiples are contained in each kind of group. Okay. The group that is a multiple of 2,401 will contain 5,764,801 multiples, because every number in this group is being multiplied by 2,401. And so there will be 2,401 squared, which is this numbers that are multiples of 2,401. Okay. In this group, there will be this many multiplications. This is because since the first number is 343, we only want to see how many of the last two numbers are multiples of 7. And we know from before that out of 49 numbers, 13 will be multiples of 7. But that was only 49 numbers though. This is a group of 5,764,801. So we multiply. Oh, Dad. Oh, I thought my dad was here. Sorry. Okay. So we multiply 13 by 117,649 to get these numbers are calculated, just to save time here. But you should be able to figure it out. Um, I multiply these numbers, right, and I add them up, and I get a sum of 67,883,473. Okay. Uh, just to reiterate, that means there's exactly a 67,883,473 out of 13,841,287,201 chance, or 0.5% chance to multiply three random numbers together and to get a multiple of 2,401. Um, and I tried it. I coded, or I got my computer to do a thing, and it's a 0.5% chance. So yeah, okay, all right. Finally, I'm just going to calculate f of p to the e for four numbers once, just to show you how it's done, um, and then that's it for this part. Uh, let's say I want to calculate f of 5 to the 3 given four numbers. What I need now are the values of f of 5 to the exponent for three numbers, which I'll reference to get our values. Um, there's 125 groups to look at here. There's four types, yada yada, right? We've done this all before. What I want to focus on here is how we determine how many multiples are in each group. Okay. This process before, uh, what we did was we ignored the first number and we treated the last two numbers like a modified version of a problem that we've done before. So I want to do the same thing here. I'm going to ignore the first number and I'll treat the last three numbers like a problem that we did before. Okay. So for example, I know that the groups that are multiples of just one will have 113,125 multiples, because that's what we found f of 5 to the 3 for three numbers to be. Um, now, okay, what about the groups that are multiples of 5? Since the first number is a 5, we kind of just want to know how many multiples of 28 we can make by multiplying the last three numbers. For this, we can refer to f of 25 for three numbers, which is 2,825. But this comes from a list of 15,625 multiplications, while we have 1,953,125 multiplications here. So I'll multiply 2,825 by 125 to get to 353,125 to adjust for the size difference of the groups. And then this is how many multiples are in this group. All right. And then the rest of these numbers are done in the same way. We multiply and add together whatever needs to be done, and we end up with an answer of 24140625. Beautiful. Okay. Now that you've got a good look at how these numbers are generated, I'll skip to where I've gone and generated the values of f of p to the e, and I'll just show them to you. Okay, so this is what it looks like for two numbers, three numbers, four numbers, and five numbers. I only generated the values up to five numbers for prime powers up to 29 to the power of 5, because I felt like this is all I need to determine what the values for two numbers first. And what we're going to do here is try to look for some patterns. What I like to draw your attention to here is that as you go up in a sequence of prime powers, right, going from p to the 1, p to the 2, p to the 3, and so on, that these numbers become more and more divisible by p. So what does this mean? Um, let's look at the fives here. F of 5 is 9, which isn't divisible by 5. 1 times 9. F of 5 to the 2 is 65, which is 5 times 13. F of 5 to the 3 is 425, which is actually divisible by 5 twice. It's 17 times 25. F of 5 to the 4 is 2,625, which is 125 times 21. And finally, f of 5 to the 5 is 15,625, which is 625 times 25. 5 to the 4 times 25, right? Generally, these numbers follow the pattern of being divisible by 5, one more than the number before it. And as you see here, well, you can see if you want, this pattern is followed by every value of f of p to the e, right? Here, and to show it, I'll go back to the powers of 5. When you divide these numbers by 5, the appropriate number of times, you get the numbers 9, then 13, 17, 21, then 25. You might notice here that these numbers are all separated by 4, which coincidentally is 1 less than 5. Now, if you look at all the values that we generated, the values we generated, they seem to follow the same pattern. So if you look at, I don't know, the 17 group, right? These all differ by 16. 23 group, they differ by 22, right? So all these groups, they follow the same pattern. Okay, now we've got enough information to generalize a formula. The numbers here, yeah, they increment by p minus 1, so they must be, an arithmetic sequence. Arithmetic sequence. So all these numbers are of the form a times p minus 1 plus b. Okay. Well, all these numbers are one more than a multiple of 4, right? You can see that. And so you can check these are all one more than a multiple of p minus 1. You can check. So they can all be written as a times p minus 1 plus 1. Okay, so look at this. So this first number, 9, is 2 times 4 plus 1. Second number, 13, is 3 times 4 plus 1. 4 times 4 plus 1. 5 times 4 plus 1. 6 times 4 plus 1. And you'll see here that the number that's multiplying with 4 is always one more than whatever the exponent is, right? So we can say that, yeah, a is always one more than e, right? So these can all be written as e plus 1 times p minus 1 plus 1. Okay. Now, you'll remember from before that all these numbers are multiplied by p a certain number of times, right? Maybe I can do this. So here it's being multiplied by 5 0 times. Here it's being multiplied by 5 1 time, and then 2 times, 3 times, 4 times. Okay, and then we see that the number of times these numbers are being multiplied by p is always one less than whatever the exponent is, right? So we can say that this is all being multiplied by p to the power of e minus 1. Okay. So finally, we have our formula. Um, and every value of f of p to the e for two numbers can be written as p to the e minus 1 times e plus 1 times p minus 1 plus 1. Yeah. We want to find out what the probability is, right, of multiplying two numbers together and getting a multiple of p to the e. It's equal to this. All right, great. So now let's look at three numbers. What I'd like to what I'd like you to notice here is that just like with two numbers, the values of f of p to the e are becoming more divisible by p as we go down the list. Uh, so yeah, so let's look at the 5 group again. Um, f of 5 is 61, which isn't divisible by 5. F of 5 to the 2 is 2,825, which is actually divisible by 5 twice. Okay, it's 5 to the 2 times 113. 5 to the 3 is equal to 113,125, which is divisible by 5. Get this, right, 4 times. Okay. And I know most of you are seeing a pattern here. This is equal to 5 to the 4 times 181. F of 5 to the 4 is this, which is 5 to the 6 times 265. F of 5 to the 5 is this, which is equal to 5 to the 8 times 365. Okay. Okay, so what now, right? Well, there's something I'd like to show you here, which is that all of these numbers are one more than a multiple of one less than that prime number that it's associated with. Okay, what do I mean by this? So look back to what we did with 5. Right, look back to what we did with 5. Um, each of these numbers, 61, 113, 181, and so on, right? These are all one more than a multiple of 4, um, right? Let's look at the 7 group. Um, all of these numbers are one more than a multiple of 6, right? Um, well, it turns out that for all of these numbers, all the ones I checked, uh, this is true. So if all of these numbers are one more than a multiple of one less than the corresponding prime number, I can subtract 1 from each of these and then divide by 1 less than that prime number to do this. And then I'll make them smaller. We can look for another pattern. Okay, so follow me here, right? The first number in each of these lists is a multiple of 3. That's 6, 9, 15. The second number in each of these lists is a multiple of 4, most of them. Yeah. The third number is a multiple of 5. The fourth number is a multiple of 6. And then the fifth number is a multiple of 7. So what happens if we divide? Okay, well, I think the pattern's clear now. The numbers in the 2 column are increasing by 0.5. The numbers in the 3 column are increasing by 1. The numbers in the 5 column are increasing by 2, and so on. Roughly speaking, the numbers that we have here are increasing by a value of p minus 1 over 2. I'll spare you the details of this, but each of these numbers can be written as e plus 1 times p minus 1 over 2 plus 1. Right, okay, so let's make our formula now. Think back to what we did before. we divided these numbers by 3, 4, 5, etc. Um, and all these numbers, right? These are two more than whatever the exponent is, right? Um, so, in other words, what we did was we divided these numbers by e plus 2, okay? So to make our formula, I'll do the opposite, and I'll multiply this all by e plus 2. Okay. Now, remember from before that we got these numbers by subtracting 1 and dividing a bunch of numbers by p minus 1. So what we want to do next is multiply this by p minus 1 and then add 1, right? And then where before we were multiplying by p to the e minus 1, you might remember that. Now we're going to multiply by p to the 2 times e minus 1 because we went up by 2 in each prime power we multiplied by instead of 1. Okay, so here's the formula to calculate f of p to the e, and here is the formula to calculate your probability. Okay, 4 numbers. All right, I'll do the same thing as I did before. These numbers become more and more divisible by p as you go down, but plot twist, they become divisible by p 3 more times than the number before it, instead of 2 more times. Again, like before, all these numbers are 1 more than a multiple of p minus 1, right? So I'll subtract 1 from every number and divide by p minus 1, which is this. And then if you remember what we did before, we divided the first number by 3, the second one by 4, so on. I'm going to do something kind of similar here, but I'll divide the first number by 4, the next one by 5, and then 6, and then so on. And we end up with this. Okay. And now we want to find another pattern. Let's look at the 13 and 19 groups here. Okay. Now, just to see what happens, right? I'm going to subtract 1 from all of these numbers. Okay. Now, since I want to find a pattern in these numbers, I'm gonna prime factorize all of them. Okay. And then, yeah, they'll look like this. Now, if you look at these numbers, in the 13 list, these numbers are all divisible by at least 6, right? There's at least 1, 2, and at least 1, 3 in this list. The numbers in the 19 list are all divisible by at least 9. Yeah, okay. So let's divide all these numbers by 6 and 9. And all right. Okay, this looks pretty nice, right? Well, why did I choose to divide these by 6 and 9? This might seem like a bit of a leap in logic right now, but the numbers 6 and 9 happen to be equal to p minus 1 over 2. Yeah, p minus 1 over 2. Okay, well, it seems like then, right, if it works for these, that all these numbers are 1 more than a multiple of that all these numbers are 1 more than a multiple of p minus 1 over 2. Okay. And you see here that if we do the same thing to every group, they are, right? From this point on, I'll just stop trying to justify the things I'm doing, and you'll just have to trust me on this. Remember before when we divided the first number by 4, the second number by 5, etc., right? I'm going to do the same thing again, except I'll divide the first number by 3, the second one by 4, and so on. And we'll have quite a lot of decimals, but believe me, this will look, a lot prettier once we do the math. this is what we end up with, right? So let me refresh your memory. Uh, with two numbers, the ending numbers differ by p minus 1, right? With three numbers, the ending numbers divided by differed by p minus 1 over 2, and then these numbers, they differ by p minus 1 over 3. Um, and hopefully now you should be seeing how all of this is fitting together. Um, okay, let's make our equation. Uh, the inside is equal to e plus 1 times p minus 1 over 3 plus 1. Next, I'll multiply this by e plus 2, just reversing all our steps. Next, multiply this by p minus 1 over 2 and add 1. Next, multiply it by e plus 3. Okay? Then multiply it by p minus 1 and add 1. And then finally, you want to multiply this by, what is it? By p to the 3 times e minus 1, and our formula is done. And then that's the probability. Okay, 5 numbers. I'll go through this quickly. First, we divide by p. We divide by p more as e gets bigger, right? This is the same as what we did before, except now we're going up by powers of 4 instead of 3. Next, subtract 1 and divide everything by p minus 1. Next, divide by e plus 4. Okay. Then subtract 1 and divide by p minus 1 over 2. Okay. Then divide by e plus 3. Right. Now, this is where we stopped for 4 numbers, but I'll keep going. Here, we want to subtract 1 and divide everything by p minus 1 over 3. Okay. Hopefully you're starting to see a pattern here. Finally, divide everything by e plus 2, and we're at the end. Okay. Now, each of these numbers are separated by p minus 1 over 4, and they're all equal to e plus 1 times p minus 1 over 4 plus 1. Okay. Now let's make the formula. First, multiply everything by e plus 2, then multiply everything by p minus 1 over 3 and add 1, then multiply by e plus 3, multiply by p minus 1 over 2 and add 1. Now multiply by e plus 4, multiply by p minus 1 and add 1, and then finally we multiply by p to the 4 times e minus 1, and this is our formula. Okay, so f of p to the e for 5 numbers is equal to this, and then if you want to find the probability of multiplying 5 numbers together and getting a multiple of p to the e, you use this formula. Okay. Now, I hope there's something that you notice here, which is that for every number we start with, the first thing we do is we divide by the proper prime power, right? Then we subtract 1 and divide by p minus 1, then divide everything, right, by some number, which is equal to e plus something, and then you keep doing this process until you get to your final number. Now, this process, it loops once for 3 numbers, twice for 4 numbers, and then 3 times for 5 numbers. And then, I'll take some creative liberty here, and I'll assume that this pattern holds for any amount of numbers. And based on this information, we can now create one big generalized formula to calculate f of p to the e for any number of numbers. Okay, so first, let me put the formula for f of p to the e for each number of numbers on the screen. Now, the first thing I want to do is generalize the formula for the inside number we always get, right? So for 2 numbers, it looks like this. For 3 numbers, it looks like this. For 4 numbers, it looks like this. For 5 numbers, it looks like this, right? And so generally, we can say that the inside number we get can always be written as e plus 1 times p minus 1 over n minus 1 plus 1. Uh, and just to simplify this, I'll call this t. T stands for the inside. Great. Okay. Next, I'll expand all the equations we had from before, and so they'll look like this. Okay. And I'm gonna clean these up a bit, so it looks like this. Okay. Okay. So you'll notice now that there's a lot of terms that have p minus 1 to some power, right? And things like e plus 2 times e plus 3 times e plus 4, going up, right? So you only see here that it goes up from e plus 2 to e plus 4, but that's only because we're dealing with, like 5 numbers, right? But if you try to find f of p to the e for a lot of numbers, you'll get, e plus 2 times e plus 3 times e plus 4, e plus 5, e plus 6, so on, right? And you'll have a lot of numbers to multiply. So what we need is a nicer way to represent this. Instead of writing e plus 2 times e plus 3 times e plus 4 here, I'm going to write e plus 4 factorial divided by e plus 1 factorial, which equates to the same thing. You also see there's some terms divided by 6, some terms divided by 2. These are because before we were dealing with p minus 1 over 2, p minus 1 over 3, etc. And so I'm collecting all the divisions and shoving them at the end of the term here. So with higher values of n, right, we'll get terms divided by 24, 120, and so on. And so I'll rewrite these as a factorial, just to this is a nicer way of writing it. Okay, we're getting somewhere. Now the question is, how do we create a formula where we don't know how many terms there are, right? Because here you see there's 2 terms, right? This and this. Here there's 3 terms, and then here there's 4 terms. And then the answer to that is that we use a sigma function. Okay. Now a sigma function, what it's useful for is that if you have a lot of terms and that they all have something in common, you can find that you can represent all these terms with just this one symbol, the sigma function. If you know how to code, I guess, if you've made like a for loop before, the sigma function, it's the exact same thing. So yeah. Now what I'm going to do is I'm going to split these equations into 2 parts, because there's one part that has the t in it. Remember, we found t that represents the inside number. These can't be a part of the sigma function because of this t. That kind of it mucks things up. But these can be represented with the sigma function. So I'll split these into 2 parts. So generalizing the first part of the formula, and what I'm seeing here is that the number of times p minus 1 is showing up here is increasing by 1 each time. And the number of times p minus 1 is, in this formula, is always 2 less than n. So for this part, right, I can rewrite this as p minus 1 to the power of n minus 2, and that covers all of that. The amount of e plus something factorial also goes up by 1 each time, but they're all divided by e plus 1 factorial. So we can write this as e plus n minus 1 factorial divided by e plus 1 factorial. Okay. Finally, we can write the last part as times t divided by n minus 2 factorial. And then now I'm going to change t back to what it once was, which is e plus 1 times p minus 1 divided by n minus 1 plus 1. And then this is the first part of our formula. Okay. Okay. And this is a part of the sigma function. So when n is 2 or 3, a sigma function isn't necessary. So I'll just look at when n is equal to 4 or 5. Okay. So I'm using the variable I as the incrementing number for the sigma function. That's pretty standard practice, right? Um, for n equals 4, the sigma function looks like this. And for n equals 5, the sigma function looks like this. I'll save you the hassle, and I'll just show you what the sigma function looks like in general here. It's a general form. Okay, and finally, we get to the end. This is what we've been working towards all this time. You can see here where I combined the two parts of the formula we created, and where I added the p to the n minus 1 times e minus 1, which represents the prime power that we always multiply everything by at the end. Right here, I put the formula for probability. If you want to find the probability for some number like 72, right? You just run 8 and 9 through this formula individually, and you can multiply the two probabilities that you get. That's about it. See ya.